And thank you everyone for being here. And I would like to thank Ricardo and the rest of the organizers for kindly inviting me to give a talk here today, and extend it to Mauro and the rest of the coordinators for this great program that you created. Thanks. So my name is Sol Carretero. I'm an associate professor at Universidad Autónoma de Madrid in Spain. And the work I'm going to present here is related to quantum levitation and optical resonators. And this work has been done basically by Professor Hernán Míguez at the Institute of Material Science of Seville, and Victoria Esteso, which is currently in the Lens Institute in Italy. So we are 3 people, now everything in a different spot in Europe, but everything started back in 2015 at the Institute of Material Science of Seville. And this is not working. I don't know why. I don't know what to do. I don't know. Anyway. Okay, nothing is working. Sorry. Sí, es que se ha quedado aquí atascado. Aquí, here. What about now? Sí, sí, now it works, I think. Yeah, now it. Okay, sorry for this. So I will start with a short introduction to the Casimir effect and the Casimir Lipschitz force. And I will highlight some aspects that are relevant for us as, well, we were working in this multifunctional optical materials group, so there are some things related to materials that concerns our work. So according to the Casimir effect, 2 perfectly conducting plates at 0 temperature will be attracted by a force, which is given by this formula here, where we can see that it depends just on universal constants and the separation distance between the mirrors due to the vacuum fluctuations, right? And because this force decreases very rapidly with the separation distance, we need to try to measure it in the nano and micro scale. The simplest way to express or to explain this phenomenon is just based on the different pressure experienced by the bodies because of the optical modes that can exist outside the cavity and those that are enabled inside the cavity. Afterwards, Lipschitz and collaborators extended this effect and considered different temperatures, and also extended it to more complex geometries, for instance, the sphere and plate geometry or the multi-layer structure. And they considered what we call real materials, in the sense that you are taking into account the optical properties of your materials. And this is important. Well, since then, there have been many different experimental and theoretical works trying to demonstrate the existence of this force and also to take advantage of this force. And one of the most interesting, in my opinion, results of this theory is the fact that in contrast to the Casimir effect, in which all the time the force is going to be attractive, in this case, in some situations, the force can be repulsive. And this opens the door to many technological applications in the so-called nano and micro electromechanical systems, in which we have movable parts at very tiny distances in these systems that form part of our everyday devices. So in the end, because of this attraction, they got stuck, and then the device stops working properly. It has also inspired biomaterials, and it has to do with microfluidics and drug delivery, as we saw already in subtalks yesterday. In our case, This repulsive force, well, we have been working on this from two different points of view. Very recently, we have been interested in their effect in icy systems and some geo or astrogeophysics, as it has to do with the escape of greenhouse gas molecules from melting ice, or it is related also to the preservation of oceans in icy systems like Pluto or Enceladus or other icy worlds. And this is a collaboration that we recently started with different works, different people in the world. So just to give you some hints of what we are doing right now, although I will focus more on the optical properties and multifunctional materials. And in 1991, Elbaum and Schick predicted the surface melting of ice being incomplete. So surface melting is the process in which a thin layer of liquid can form at the interface between a solid and its vapor, and it can grow in thickness as the triple temperature is approached. And what we observe is a solid that melts from its surface inward. So in their prediction, they found that at the triple point, this liquid layer could be only as thick or as large, it depends on what the landscape, as large as 3.4 nanometers. And this has different implications. For instance, if you want to have some habitats in them, the thickness of the water layer is important. So what we did next was a theory in which we could vary simultaneously the ice and water layers in a 4-layer system, having a solid, a rock, for instance, here. And well, what in our model, what we observed is that that not only the Elbaum and Schick is permitted here, like this stable layer thickness that they predicted, but that depending on the initial conditions of the thickness of the ice and the water, a different stable situation with much thicker films of water could be found. So depending on the initial conditions, you can move to these different stable positions. In another work that we have been working recently, we demonstrated that it is necessary to have an ice coating of nanometer or micrometer length scale around what are called the gas clathrates in order to maybe, well, this is a model in which we try to propose the insulation of oceans in Pluto or the composition of the rings in the moon Enceladus. No? And this is all related to, sorry again, to gas hydrates. So clathrates is a chemical substance that consists of a lattice that can trap or host other molecules. In the case of a gas hydrate, the host molecule is water and the guest molecule is a gas. And basically, these systems can be stabilized outside their window of thermodynamic stability if they form a nice layer around. So these are some works that we have been doing in the last years. But here, I would like to show you some results we also got about quantum trapping and levitation. I didn't say this, but we started in this research line back in 2015, the three of us, from scratch. And we said, okay, we realized that there is this force that depends strongly on the optical properties of the materials. We are all the time modifying the optical properties of our materials in solar cells, optical resonators. Maybe we can contribute somehow to the field. So we had a few papers, and we have a gap here of 3 years. And this is what I would like to show you today. We had a nice idea with a bittersweet ending. And well, because this is not shown in the papers, I would like to share this today with you. Jeremy Mundai gave a nice talk yesterday and also showed something like this, like a timeline of the experimental evidence. And I'm going to be much more brief and trying to go to my motivation, okay? So after the prediction of the Casimir effects and the Lipschitz extension, there were some experimental attempts to try to demonstrate the existence of these attractive forces, but the technology and the precision of the measurements was not enough at that time. So after this technological development, with the use of a cantilever in the sphere plane and with two plates, it was possible to finally demonstrate the existence of an attractive force with the experiment of Lamoureux, basically. 4 years later, in 2009, repulsive Casimir forces were also demonstrated experimentally in the sphere plane configuration. And then in 2015, when we started this project, we said, okay, what about the repulsive forces in the plane-plane geometry, but without the use of this cantilever? So the reason why there were some difficulties in demonstrating the existence of this force is not just related to the technological evidence. There are other difficulties, as it was recently shown also or summarized by Palacios and Svetovoy in this recent paper. So you have to deal with double layer forces that can mask the presence of this force. You also have the effect of the rugosity. So if you want to go to very short distances between the interacting objects, it might play a major role. And you also have these pad potentials, which are like special variations of the electrostatic potential on your samples. So along these lines, there have been many proposals to try to manipulate the Casimir force, both from the theoretical and the experimental point of view. Also, Jeremy Mundai gave some examples yesterday with the geometry, where you have a hole, and then you have an object that goes through it, by the employment of metamaterials, the linear and non-linear optical properties of some materials, also with nanostructurations, creating these slit arrays that we've seen in the program as well, with the phase change of some materials. So George Palacios in this paper, they have a material that can change from crystalline to amorphous, and with a laser light they do this, so the optical properties are changed, and therefore the Casimir force is also changed. There have been some attempts trying to play a little bit with the magnetic properties, and also superconducting materials, tuned materials as graphene, or as we saw yesterday with epsilon near zero materials. So I'm not going to give the details of this experiment also because Jeremy Mundai gave a lot of details basically about this, but just some tips again to remember some things. So most of the experiments were done in the sphere plane geometry. Basically, you have, in the case when you have two similar materials interacting, you are going to have a repulsive force, so you are going to be this as a signal, this deflection signal. Whereas when you have two dissimilar materials interacting, and for certain materials, a range of parameters, and so on and so forth, the force that is interested in mediating the interaction will be repulsive. So in our approach, when we started, well, you cannot see it very well maybe, but we came with a novel approach. We wanted to demonstrate macroscopically this quantum effect. And for this, we wanted to skip the cantilever approach and propose something different, in which we are going to grow an optical resonator in which one of the mirrors is levitating in a fluid, and by means of spectroscopic measurements, infer indirectly the Casimir force. So this is going to levitate because of the balance of repulsive Casimir forces, and then of course buoyancy and gravitation. So how do I get a repulsive Casimir force? Well, in the case of a plane parallel geometry, it is well known that if you have a dielectric function epsilon minus 1, 0 or 1, and if all your materials fulfill this inequation, it is possible that your force is going to be repulsive. But note also that this inequation is written in Matsushita frequencies. This means that we are rotating to the real axis to the complex plane, so that we are eliminating these rapid oscillations in our integrand, and everything is going to be much easier. So when we do this rotation, we need to integrate the imaginary part of the dielectric permittivity over a wide spectral range. And this also is a huge condition for us to make an experiment, because you don't always know the optical properties of your materials in such a large spectral range. So in addition, some of the intuition that at least we could have with these solar cells and things that we were doing was missed. So for instance, if you have a look at the extinction coefficient here, which is related just to the imaginary part of the dielectric permittivity, anytime you have high absorption peaks, your curve in Matsushita frequencies will have these steps here, whereas when you have a planar curve, you have these plateaus here. And now you need to make some library of materials that can interest you, because you can handle them easily in the lab. They are chemically stable or stable in time, and so on. And this is what we did. We made some kind of libraries trying to, well, we analyzed some polystyrene, silica, or Teflon, a lot of alcohols that then we didn't take into account because they evaporate very easily. And then we have to find some sets of materials that will give this repulsive force. No? So we had, as I told you before, some experience when growing optical resonators, multi-layer structures, or with composite materials. So we could, for instance, include luminescent species in a mesoporous film in between two mirrors. And by modifying the local density of the states, you can modify basically the optical properties of your system. We could also endow these perovskite solar cells with colorful, with colors by including one-dimensional crystals, or we included disorder in dye-sensitized solar cells, and we could have record efficiency flexible solar cell. So now I'm going to focus on these optical resonators, and then Victoria is going to give a talk on these other two topics next to me. So just to give you the idea, so what we want to do is to design the optical resonator so that this upper part is going to levitate over the substrate because of this balance of forces. Then we want to find some sets of parameters, geometrical parameters, so that they are going to display a clear optical response, because we are going to characterize them spectroscopically. We will have this kind of measurements, and what we want to do is to make a fit of the optical response so that we can finally know what is the levitation distance of this system, and then go back to the original designs and see if they fit, basically. We will just employ the expression of the Casimir force for multi-layer structures, where you have an object, another multi-layer object, everything immersed in a fluid, And then we have the multiple Fresnel coefficients of the lower and the upper part of the fluid. And then this also depends in turn on the simple Fresnel coefficients. It's just for the optical properties. In this case of the optical resonator, we will just use the transfer matrix method and link it to a genetic algorithm to do the spectral fitting. So this started back in 2015. So what we found at that time is that thin films of, theoretically, thin films of Teflon, silica, and polystyrene immersed in glycerol over a silicon substrate could levitate. So the force, here I plot the Casimir force, but the total force, just shift this a little bit. So anytime the total force is 0, your system is levitating. We find that for silica plates, this equilibrium distance is stable because you have repulsive Casimir forces at short separation distances, which is here, and then gravity and buoyancy, well, gravity in this case brings you the system to the bottom, no? And then in the case of polystyrene, for instance, we have the other behavior. This is an unstable equilibrium position. We have attractive forces at short separation distances and repulsive ones at large separation distances. So having this in mind, we did other works, like Victoria will show you next, and we designed our optical resonator. What do we have to take into account? Well, an optical resonator is basically, you have two planar mirrors, and one of it is slightly transparent so that some light can go through. Then you form a standard wave here, and then the spectral response has this typical pattern where you have high reflectance bands, and then you have these sharp minimums, and this minima, the position, depend on the refractive index in between the mirrors, and then the distance, the separation distance, of course the angle of incidence, and then the order of diffraction. So in our design, one of the most important things was to create high Q factor optical resonators, and they had to fulfill all these conditions. We wanted repulsive Casimir forces with sharp spectral features in the optical regime, with well-known materials that we could handle in the lab and that we could do our estimations, that, well, exactly this, and everything in the microscale, and that was stable in time. So here I show you some results for some representative geometrical parameters, because the final design is something like here. We have a bilayer of polystyrene with a thin layer of gold immersed in glycerol over a silica film on top of a gold substrate. And here I plot the total force acting on the system as a function of the separation distance. So the yellow curve corresponds just to the Casimir force, and this also takes into account gravity and buoyancy. This is plotted in the logarithm scale because it is easier to identify this minimum here, which corresponds to the equilibrium distance at which this system will levitate. We have repulsive forces at short separation distances and attractive ones at long ones. We also analyzed the effect of electrostatic forces by employing the Poisson-Boltzmann methodology. And we found that for monovalent salt, in this large concentration, the equilibrium position was not modified at all. And even with low salt concentration, the equilibrium distance was hardly modified, despite it also enhanced the repulsiveness of the system, in the system. So this is it. We compute the total force. We look for the zeros here. We have the cavity size, and then we have the equilibrium distance, because the cavity also contains the silica film. And we could manipulate or to tune the separation or the equilibrium distance by modifying all these geometrical parameters here. No, we modify the gold thickness, the polystyrene film thickness, or the silica thickness, And then we could tune the equilibrium distance from 50 nanometers to 400 nanometers, for instance. So this is actually the approach we are going to take. We will create one bilayer, and then we are going to test it over different substrates of different silica thicknesses. This is how it would look like for 100, 800, and 600 nanometers thickness of layer. This is the reflectance response, and we can observe what we were expected. We have this sharp minima in the reflectance that grow in number and get narrower as the Q factor is changing, so as the cavity size is enlarging. One point of our design, or the strength of our design, is that you need to have high Q factor optical resonators to really say that what you are observing is levitating, because otherwise what I'm showing here in gray is the reflectance with 5% error, which could arise from, well, anything coming from the experimental measurement, and you could not distinguish systems that are levitating from those that are not levitating, which are these ones here with these other curves. Whereas when you have a high Q factor optical resonator, this is accurately described, and just one set of parameters is going to fit your optical response. This could, well, very fast. This could be used for optical sequencing with some nanometer precision, because now you have something that is levitating and can be moved. And the same for temperature. So I come now to the bittersweet part. So we started fabricating our system. We started with the upper part, the levitating part, the polystyrene and gold bilayer. So we could we had a lot of control on the thickness of the polystyrene layer. We also tried different approaches for the deposition of gold, either by sputtering or by thermal evaporation. Of course, we ended up using this approach because we did a lot of tests, and the optical properties of this system was what we expected. We had the gold polystyrene bilayer. This is how it looks like with the naked eye, and these are like the range of parameters we could consider. We characterized them, and then everything was fine with the bilayer. Then we went to the fabrication of the substrate, the gold plus the silica substrate. First, we started with a silicon wafer, and we also considered the gold substrate, and again, everything was kind of fine. We could grow easily some thickness between, well, 60 nanometers to 80 nanometers, more or less. And it is also, here you can see already an optical cavity. And then we combined everything together without glycerol. So we have an optical resonator, or in the dry system. Now we have the bilayer on top of the substrate. This is how it looks like. This is the reflectance spectrum in different positions of the sample, and we have this minimum here of the optical cavity, and then some oscillations related to the polystyrene film. The fitting with the theory was excellent, so we knew the exact thickness of the layers, and we put this into our transfer matrix code, and everything was fine. This is how it looks like. Also, we can see this optical cavity. But then we tried to include the glycerol, and when we did this, we had some problems. So we started putting a drop of glycerol close to the dry optical resonator, so that by infiltration, and because we are going to have these repulsive Casimir forces, we thought, okay, maybe the glycerol can come in between the levitating part and the substrate. And this is how we had like a drop of water with some glycerol in a different concentration, and then we evaporated the water, so everything was glycerol down the sample. And we also characterized the reflectance, and we could see that the minimum was moving, so everything looked kind of okay. But then we wanted to immerse the whole thing in glycerol, and then things started to mess up. So they rolled up with the evaporation, with this, probably because of the mechanical tensions we had in the sample. The flatness was better, but of course we were not going to use these samples. We checked literature and we found this is quite a standard, this rolling up, and it is actually used like for drug delivery. You hit this roll and then it spreads, and then you can release some drugs, or you can do some kind of lithography. We were trying to find solutions to find the flatness of our samples. We tried other solutions. Okay, let's try to do the gold more hydrophilic, so that we minimize these tensions in between the polystyrene and the gold, which probably is related to the different Young modulus of the two materials. Still rolling up. We tried acetone to try to maybe just remove the polystyrene, but it didn't work out. Okay, let's try a tri-layer of polystyrene. So I have some mechanical tension here. I will have it also here. So maybe it gets flat. But of course, now the force is attractive in between these two materials, and because of buoyancy, it was going to float. And then we also consider HF, so that maybe because of the way we we deposited the polystyrene film, then we included it into water, immersed it into water with a certain angle so that it could be released. So maybe something was going on when we in that procedure, so we tried a different one with HF that is going to eat the glass. So you can do this differently, but everything was basically the same. We changed our model or design. We considered then water. So in this case now the force is going to be attractive, but we said, okay, let's try to observe macroscopically this quantum effect, although it is not repulsive. But anyways, well, we had a cavity, we had a fitting, we had a very large cavity. Well, you can see it already with the peaks, no? We checked also what we could expect from the electrostatic forces, and what we had to observe, which is this simple minimum here of 1 order of magnitude less than the observed cavity. Well, we couldn't, we were struggling with all these problems. And then it just happened, as it always happens in science, or many times happens in science. The same idea was demonstrated experimentally by the group of Professor Xiangsang here in Berkeley. So basically, instead of doing this macroscopically, they went to micrometers. So they had a flake of gold in ethanol on top of a substrate, which is gold with this Teflon layer. So they made these spectroscopic techniques, measurements. They fitted everything, and by changing the thickness of the Teflon, in our case the silica, they could tune the equilibrium distance of this levitating gold flake. So the difference between them is best, first of all, these are micrometer scale, the flake. There is ethanol that we did not consider because of the evaporation problems. They considered also Teflon that we also did not discard it because of the electrostatic force and the carboxyl groups that can be transferred and so on. But it just worked out very well. We just proposed our theoretical designs, and then very recently the group of Timur Shegai also demonstrated in a similar way, also with gold flakes, the possibility of creating a Fabry-Perot cavity based on this idea of Casimir forces, but in this case the balance is between a repulsive Casimir force and an attractive electrostatic force. and they can go into the strong coupling regime when they include an excitonic material, basically. And so this is it. I would like to finish here. Well, I showed you some work that I couldn't show otherwise, and that took us 3 years with our designs. I would also like to bring your attention to some conference in August in Manchester, taking place, organized by Victoria, Mauro, and some others that are not here. And I would like to thank the funding, Hernan and Victoria, and you for your attention.
Okay, is there any question?
Just about, in one slide you said you use a genetic algorithm to adjust the optical properties.
Sorry?
You said you used a genetic algorithm to adjust the optical properties?
Yeah, to minimize the difference between the measured spectrum and the transfer matrix calculation. So to fit, in the end, you cannot really say the thickness of my materials are exactly these ones. So this is where the algorithm, the genetic algorithm, played a role.
Okay.
Thanks.
Hi, Sol. Thank you very much for the talk. At the end of the day, it seems that the experiment work that Professor Shang worked with materials that you discarded from the beginning. Can you comment a bit on why in their case it worked and you excluded them from the beginning? Can you give more details? You said a few words, but can you probably elaborate a bit more about that?
Well, actually, when at the very beginning, when I showed you this library of materials, let's say that we created, no, I don't know where they are, like here. So there are many combinations of materials that are well known and that you can consider for your designs. So, and then the relation in between the curves of the solids that are going to interact and the liquids are pretty much the same. So you could consider, like in the case of Capasso and Jeremy Monte, they were using this bromobenzene, for instance. There are other alcohols, but this evaporates very easily. So we were going to do this in an open system that was going to do nothing. So we just had our microscope and our samples like this big, and this is what we wanted to check. And because in the end you need the whole system to get to the final state, maybe in between there is some evaporation, so we didn't want to have this as another issue. And then the Teflon was also in our initial I don't know, here, yeah. We considered Teflon in our initial designs in 2015, but then we were checking literature and it was reported many times that you have a strong electrostatic force because of the carboxyl groups that can be transferred to the opposite surface. And we said, okay, let's keep it and take polystyrene and silica, which are, well, you can always have some oxidation. This is true, but this is the reason why we decided to not consider it. It worked for them. They characterized the effect of the electrostatic force, and it is all reported there. And then, of course, they don't have any mechanical issue. Just they synthesize the flake directly, and that's it. But we wanted like to have something macro. That was a nice idea. Didn't work out.
Have you considered using magnetic flakes?
Magnetic?
Because then you get an additional repulsor component to help you out.
No, that's an interesting idea. Thanks. We can discuss later. Thanks.
Any other question?
Very nice talk. I want to go back to what you mentioned at the beginning. We discussed this a little bit before on the ice problem. Do you know, let's say if you go to very low temperature, you still always have a layer of water there, or this is only near the melting point? Like,
I don't think so, right? If you go down to the below the, yeah, you need to be in the triple point to have the three material, like the vapor, the liquid, and the ice at the same time. So you go to lower temperatures. I don't know. We would need to. I don't know what's going to happen. Sorry. Thanks.
Thank you.
Yeah, over here.
This is maybe a naive question. I'm just wondering that if you have something in liquid, it would seem like there are many other forces other than the Casimir forces. I don't know if anybody asked that question already. So how do you know in many ways? I think for the practical reason that you want to levitate, how do you know that the Casimir forces are dominant in these cases, in these situations?
Well, we were assuming that the whole system gets to that equilibrium state so that you don't have anything related, like, so for instance, now if you have something flowing in the fluid, of course, we are neglecting all these stokes, or this is not a sphere, but all these forces are not, so the only forces we were assuming that could play a role were Casimir forces, electrostatic forces, and then gravity and buoyancy. What others would you, if it is static, what are you thinking about? Like,
for example, are among the forces that you consider, such as buoyancy and stuff, do the Casimir force dominate over those forces, or?
It dominates, yeah. So there is a small, so we always compute the Casimir resistors and then the buoyancy and gravity, and you have a slight shift of the curve, basically.
Another question on the other side.
Thank you for your talk. How the force is modified when you have a tiny change in the parallelism? If you change a little bit the parallelism, how it changes the force?
We didn't evaluate this. If everything was okay, so the good point of this is that the balance of the forces is going to give you the flatness of the film in principle, if it works properly. If you have something that is tilted, of course, things will be different. But our assumption was something like this: like if everything is working okay, the forces will be the same everywhere. This is in a fluid; it can adapt, and you have exactly you don't have to force the parallelism. It will go to the parallel situation. We believed. No.
Let me ask another different question. In the beginning part of your talk, you talk about surface melting. Can you comment on how that's related to this Casimir?
Well, it is something that we've been working very recently, and I'm not an expert at all, I have to say. I'm not an expert at all in general. So there is this work by Elbaum and Schick in 1991, where they predict that because of, they present this theory of modeling that can explain the incomplete surface melting of ice based on the action of repulsive Casimir Lifshitz forces acting at the triple point between the vapor, water, and ice. So there is this PRL that I can show you if you want. And based on this, there's been some new modeling and yeah, and theories, no, that what could happen. So. With I don't know exactly, to be honest. Maybe Kimball can.
Sorry for interrupt.
He's been working more on.
Sorry for interrupt, but we had to change.
Ah, okay.
Yeah, we had to finish the talk.
Sorry.
So maybe you can keep discussing later.
Yeah, I've been working with Kimball these days, so maybe.
So
thanks.
we can thank Sol again for thanks.